Good morning friends, this is the new section Basis for Matrices, and in this section we are going to understand how to find the basis for the matrices, right? Now the assignment 1, here are some remarks, let's read them. Real matrix of type 2 by 2 means A is equal to A, B, C, D. These are the elements of the matrix. Where A, B, C, D belongs to R, R means real because the matrix given is to be real matrix. So A, B, C, D are your real numbers that belongs to the set of real numbers. Now if your matrix is of the type 2 by 2, which means you have number of rows 2 and number of columns is also 2. So here if you see, the number of rows are 2 and number of columns are also 2. This 2 represents the number of rows and this 2 represents the number of columns. If I am having 2 by 3, which means the matrix is having number of rows equal to 2 and number of columns are equal to 3. Next, real symmetric matrix. Here, if I take A equal to A, B, B, C, if I take the transpose of this matrix, then I again get my A, right? Such kind of matrix is symmetric matrix, right? Where A, B, C are again real numbers because it is real symmetric matrix. Then third is real skew symmetric matrix. In this case, if I take A to be as 0, negative A, 0, if I take the transpose of this matrix, then the negative of that transpose will back gives A, right? Suppose let's take the transpose of this matrix. A transpose is equal to, how to take the transpose? The row is 0 and negative A. The row becomes your column. Then second row becomes your second column, right? If you take the negative outside, you get negative of 0, negative A, 0, which is nothing but negative of that A. So if A is equal to negative of A transpose, then such kind of matrix is skew symmetric matrix. Let's do the examples. Example 1. Let V be the vector space of all real matrices of the type 2 by 2 over the field R. Find a basis for V. So here, what kind of matrix is given to us? It is 2 by 2 real matrix, right? So by hypothesis, let's take V equal to what kind of matrix? 2 by 2 matrix. So that is A, B, C, D. This is the 2 by 2 matrix where A, B, C, D belongs to real numbers as it is given that this is real matrix. Now to find the basis for this matrix, for this V, we have to first take one element from V. Let's find out the generators of V, right? Okay, so let me take the element as A, B, C, D from this V. Then this matrix A, B, C, D. Now this matrix can be written as A 0 0 plus 0 B 0 0, then 0 0 C 0, 0 0 0 D. If you add all these, you will get A, B, C, D back. Okay, next what I'm going to do is I take A common from this first matrix, then I take B common from the second matrix, then C, then D, so that I can get the linear combinations of some matrices. So this is, if I take A common, this will become A 1 0 0 0. If I take B common, this will become 0 1 0 0. And then C, it is 0 0 1 0, and then for D it is 0 0 0 1. Now if you look at this, I got A, B, C, D matrix as the linear combinations of these matrices, and So can I write that A, B, C, D, this matrix is a linear combination of these matrices, which means these matrices are now generating set. So, but ABCD was arbitrary, which means every element of V is a linear combination of these matrices, which means V is generated by these matrices, right? So, first thing is over for the basis. First condition has been proved, that we have to write every element of V should be linear combinations of some matrices. Now, second condition for the basis, we have to check these matrices should be linearly independent. Then only we can say that by these two conditions, these matrices forms the basis for V. So now let's take the linear combinations of these matrices equal to 0 and find out whether these are linearly independent or not. Whether all the scalars coming out to be 0 or not. Let me take my scalars to be alpha, beta, gamma, delta. So alpha 1 0 0 0 plus beta 0 1 0 0 plus gamma 0 0 1 0 plus delta 0 0 0 1 equal to 0 0 0 0. Now if I add all these, I get alpha, beta, gamma and delta to be equal to 0 0 0 0. From here I get alpha equal to beta equal to gamma equal to delta equal to 0, which means all the scalars are coming out to be 0, which means all these matrices are linearly independent, right? So from 1 and 2 we say that because these matrices are generating set, right? V is generated by these matrices. Also these are linearly independent. So from 1 and 2 we say that such matrices they form the basis for V, right? Okay. Next, example 2. Let V be the vector space of all real symmetric matrices of the type 2 by 2. Now the matrices are given to be real symmetric. Find the basis for V. So by hypothesis, we have to take the kind of the real symmetric matrix. So V is equal to, let me write V as real. For real symmetric, what is the condition? That A transpose should be equal to A. So I write the matrix as A, B, B, C. Okay. Now, to find out the basis for these matrices, to find the basis for these V. Okay, let me take one element from V, A, B, B, C. Okay, so I have to take the linear combinations. I have to make, how can I make the linear combinations for this matrix? A, B, B, C. Again, can I write this matrix as A 0 0 0 plus 0 B B 0 and then 0 0 0 C. Okay, now if I add all these, I get A B B C back. So I can write this matrix as a sum of these matrices. So this is equal to taking A common 1 0 0 0 plus taking B common 0 1 1 0 plus taking C common 0 0 0 1, right? So this A, B, B, C is now written as a linear combinations of these matrices, right? So therefore A, B, B, C is a linear combinations of these matrices, but A, B, B, C was arbitrary, which means every element of V is a linear combinations of these matrices. Thus, V is generated by them. Now to check these matrices are linearly independent or not. Let me take the scalars. Alpha 1 0 0 0 plus beta 0 1 1 0 plus gamma 0 0 0 1 equal to 0 0 0 0. If I add all these, I get alpha beta beta gamma equal to 0 0 0 0, which means alpha equal to beta equal to gamma equal to 0. So these matrices are linearly independent because all the scalars are coming out to be 0. So from 1 and 2, these matrices forms basis for V. Simple? Okay. Next, example 3. Let V be the vector space of all real skew-symmetric matrices. Alright, now this time I am having the real skew-symmetric matrix of the type 2 by 2 over the field R. Find the basis for V. Let's find out the generators first and then check those generators to be linearly independent or not. Okay, because the matrix is now going to be skew-symmetric matrix, so by hypothesis, let's take V to be equal to the matrix of the kind 0, A, negative A, 0. You can write here negative also, it's your choice. I'm writing negative A here this time, where A is belonging to R. Okay, let's take one element from V. Okay, so I'm taking the same. How can I write this? Taking A common, this can be written as 0, 1, negative 1, 0. Okay, which means this is the linear combinations of 0, 1, negative 1, 0. Only one matrix. Okay, so which means 0, A, negative A, 0 is a linear combination of 0, 1, negative 1, 0. But 0, A, negative A, 0 was arbitrary. Every element of V is a linear combination of this matrix. Thus, V is generated by this matrix. To check whether it is a linearly independent or not, for that I must take one scalar because I am having only one matrix. So, let alpha be that scalar. So, alpha into 0, 1, negative 1, 0 is equal to 0, 0, 0. Okay. Now from here, can you see that this matrix can never be 0? Right? 0, 1, minus 1, 0. Of course, this matrix cannot be equal to this 0, 0, 0 matrix. It cannot be equal to this matrix is called 0 matrix. So this cannot be equal to 0 matrix, which means alpha is 0 then, which means scalar is 0 then. Yes. So therefore, this matrix is linearly independent. I got my scalar to be equal to 0, so this is linearly independent. So from 1 and 2, we say that such kind of matrix is a basis for V. So I am having only one basis for such vector space. Okay. Thank you so much. In the next video, we will do some more examples like this for real diagonal matrices, for upper triangle matrices. There are many more forms of matrices. Okay. So thank you. God bless.